All right, so we're going to use several different applications. I'm going to show you several different formulas that you can use when dealing with logs. We're also going to go back into the natural number type functions. Okay, so whenever we're dealing with population growth, so I'm going to give you some formulas, so make sure you write these down. So population growth. So remember what I said before about the natural number is anytime you have growth or decay, the natural number comes into play. So with population growth, what we're doing is we're figuring out mathematically, on average, how much population grows in our world, all right? So on page 107, you have a couple blanks, and I'm going to give you the numbers for that. So in 2020, the U.S. population is 331 million, roughly. Yeah, 331 million. Okay? Now, the function that we're going to use, it says, is approximately blank million people. So in that blank, you're going to write 331 million. So what that does is it eliminates all these zeros. We don't have to use them. Okay? All right. Then the exponential growth rate in 2020. So the growth rate right now is 1.78%. So this is in the year 2020. Okay, so we have approximately 331 million people in the United States, and the growth rate is 1.78%. Okay, all right, so the population growth formula is going to look familiar to you. It's A of T equals A sub O E raised to the KT. Okay, so let me get rid of these numbers. All right, so let me tell you what all this means. This is just like your continuous growth formula. It's the exact same setup. There's no difference at all. It's just that the variables mean something different because we're not talking about money growing. We're talking about people, the amount of population growth. So A of T just means the ending amount in terms of time. So this is our ending amount. This would be like our y variable. AO just means our beginning amount. So anytime you have what's called a subscript, what that tells you is the position. So this is the amount at 0 years. So what you put into it, what your beginning amount, like in the continuous compound interest, this is the beginning amount of population that you're starting with. The K is your growth rate. So this is our percent. And remember, you have to change the percent to a decimal. So make sure it goes to a decimal. Otherwise, it won't work. And then T is our time, and again, in years. Okay? So it really is the exact same setup. Any type of growth formula is very much the same. If you look at number 20, you have a volume decay problem. It's exactly the same as a continuous compound interest one. All right, so remember our beginning amount was 331 million. We don't need all the zeros. Our rate is 1.78%, so 0.0178. And they want to know what is the expected population of the U.S. this time in 2025. So because this number is based on 2020, 5 years from now is what we're looking for. So it's times 5. So our time is 5. And we want to know what's the ending amount. So the ending amount after 5 years. Okay, so all you have to do, get your trusty calculator, do 331 times E raised to the 0.0178 times 5. Make sure it is in parentheses and make sure that you close the parentheses. And it's going to equal, so the amount of population after 5 years in 2025 is going to be approximately 361 million. Okay, if I rounded it, it's because it's 361.8, so you can do it that way, or around 362 million. I would accept either answer. Okay, so that's how you use your population growth formula. Then the second question for this one says, when will the population hit 500 million? So think about your numbers. 500 million is the same, so I'm going to erase this. 500 million is the same as 500 million. Okay, 500 million, 500 million, same thing. So you can name it two different ways. So now the question is, when will the US population hit 500 million? So we go 500 is what we're ending. We started with 331. We still have a growth rate of 1.78%. We are now looking for time. Okay, so we're right back to what we did with our ln and e lesson. We're going to isolate my e, so I'm going to divide both sides by 331. And I get 1.51 equals e raised to the 0.0178t. Got to get rid of the e, so I'm going to ln both sides. That cancels it. So I have ln of 1.51 equals 0.0178t, and then I'm going to divide off that 0.0178. Now I can figure out what t is. So I'm going to do ln of 1.51, make sure you close it, divided by 0.0178. So my time is about 23 years. Okay, so if in 2020 we had 331 million, 23 years from now, so in 2043, we'll hit 500 million. Okay? All right, now number 20 is exactly the same thing, same setup. It's still a growth and decay type problem. The only difference is, since it's decaying, so it's a radioactive decay, I believe. Oh no, how much the how much drug is in your system, and that drug is decaying. That's what this one is. Okay, so we have a model. V equals V sub O, E raised to the KT. Again, exact same setup. The V is the ending amount of volume. VO is the beginning amount. K is the rate of decay. And T is the time. So same exact setup. So the question is, if 10 milligrams of volume decays to 5 in 36 hours, find the rate of decay. Okay, so it decays in 36 hours. So because we started with 10 and we ended with 5, that's where you have to be careful. If 10 milligrams decays to 5, so 5 is our ending amount. We started with 10. We are looking for the rate of decay in 36 hours. Had to read it. Okay, so there's our problem. We started with 10 milligrams. After 36 hours, they checked again. It was down to 5 milligrams. So what is the rate of decay? So same thing. You're going to divide off the 10. So I get 1/2 equals e to the 36k, just switching that. I'm going to ln both sides, cancels my e. So I have ln of 1/2 equals 36k. I want k by itself, so I'm going to divide both sides by 36. So ln of 1/2 divided by 36 is a negative 0.01925. Okay? Now, if you notice, this is the first time you've seen a negative for a rate. So the rate of decay, anytime you have decay, your rate will always be negative because it's lowering the amount. It's going from a high number down to a low number. So if you think about a decrease, a decreasing slope, right? That's what's it's a negative slope. So this is it's decaying at the rate of 1.9%. Okay, just under 2%. So it's going down 2%, almost 2% every hour. Okay, so this is growth, any type of growth or decay problem. The next type of problem you will see in your chemistry and biology classes. So pay attention, especially if you're in the nursing field. So this is called a pH scale. So the pH scale is negative log times H, or of H plus. Okay, so here's what all this means. pH is it's a scale that determines the acidity or the alkalinity of certain products. So for instance, if you think of a lemon is pretty acidic, okay? So it is going to have a lower number than 7. So anything below 7 on the pH scale is pretty acidic. Anything above 7 is what they call basic or alkaline. So an example of that would be like baking soda, something that kind of lowers the pH value. So the higher the pH value, the more basic or alkaline it is. The lower the pH value, the more acidic it is. Okay? So this is our formula to find our pH. The H plus is what's called hydronium content. So H plus, the plus really doesn't mean anything. It's just a symbol for hydronium. And this is where you are going to use your scientific notation for this. So just a reminder, if you had 3.21 times 10 to the 4th power, what that actually means is your decimal is 4 places to the right because it's making this number bigger. So 32100. So I take my decimal and I move it 4 places. Okay? So positive exponent means I have a bigger number. If I had 2.78 times 10 to the negative 3, what this means is my number is actually small. So I'm going to take my decimal and I'm going to move it 3 places to the left. So 0.00278. So negative exponent, you have a small number. Positive exponent, you have a big number. And this is, you're going to use this. The hydronium will always come in scientific notation. One thing to be aware of is scientific notation on your calculator has the symbol EE. So again, if you had 2.78 E to the negative 3, that's what that's actually saying. That E indicates it's in scientific notation, and the number after the E is the exponent on 10. Okay, so let's see. Root beer has a hydronium ion content of 9.16 times 10 to the negative 4 moles per liter. What is the pH value? So we're going to use our formula. They give us the hydronium. We are looking for the pH value. So it is 9.16 times 10 to the negative 4 moles per liter. It's just a unit of measure. So we have to find the pH value. Well, pH is already by itself. So you don't have to do anything to solve for it. All your work is right here. So you can do it one of 2 ways. You can either just enter it just like this. Just remember that you will use your EE button for scientific notation. Or you can change it. I'm going to move my decimal 4 places to the left. So 0.1234. Okay, and you just plug it in. Negative, make sure you use the negative sign, not the minus sign. Negative log 0.000916, close the parentheses. So my pH value for root beer is 3.039, or sorry, 38. So we're going to round it to 3.04. So this is root beer. So I'm going to write this over here because we're going to need it again. So root beer has a pH of 3.04. Okay. Then it says the pH of ammonia is about 11.5. What's the hydronium? So now they're giving us the pH value. So 11.5. So 11.5 is higher than 7. So ammonia is pretty alkaline. It's pretty basic. Okay. Negative log. And now we're looking for the hydronium. So with this, you can't do anything with the log until it's by itself. So you're going to divide off the -1. So I have negative 11.5 equals log of hydronium. So now you're given a log. You're going to take it back to an exponent. So 10 raised to the negative 11.5 is going to give you the hydronium. So remember, you're just rearranging. Okay? So now all you have to do is plug that back into your calculator. 10 raised, and this is where you can use your hat key, to the negative 11.5 is 3.16 times 10 to the negative 12. Now, this is what it looks like. 3.16222, blah, 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 E negative 12. That's what it's going to look like on your calculator. But this is in scientific notation. Okay, so the EE just means it's 10 raised to the negative 12. Okay? Okay. Then another question, 23 on page 108, says determine the pH of lemon juice if the hydronium is 3.98 times 10 to the negative third. Okay, so we're looking for pH. We're given the hydronium. So again, you can do either plug it in straight through as a scientific notation, or some of you, I think on the TI 30s, there's an actual key that says 10 or times, so an X, times 10 raised to the negative X value. So you can actually use that button. So we're going to go negative log of 3.98 EE negative 3, and then close the parenthesis. So with a lemon, the pH is 2.4. And then remember the question says, for acid reflux diet requires foods and drinks with pH higher than 5. Would root beer or lemon juice be allowable for this diet? So no, it would not, because they're both below 5. They want it above 5. Okay, so that's the pH formula. The next one is for earthquakes. It's how they calculate the Richter scale. So R stands for Richter scale, log of X over 0.001. Okay, so X is the intensity of shaking. So in California twice, I was in 2 different earthquakes that were 7.1. In the one in 1989, it was during the World Series. It was the Giants versus the Oakland A's, the San Francisco Giants versus the Oakland A's. And they were just getting started with the World Series. I believe it was the 2nd or 3rd game. And it shook so much that we had, in San Francisco, they had two-level freeways that collapsed. So it collapsed on about 40 cars. Part of the Bay Bridge, one section of it fell. So it's also 2-story, and one section of it fell like this. I lived in Santa Cruz at the time, and we lived 2 blocks from downtown Santa Cruz that had a bunch of old buildings, and all of those collapsed, and 2 or 3 people died downtown. It was a very stressful time. Very, very stressful time. So I am so glad I'm in Texas and don't have to deal with earthquakes anymore. So R represents the Richter scale. So when you hear of an earthquake, they give it to you in 3.1. The one in Santa Cruz, that was the Loma Prieta earthquake. It was a 7.1. The X is how much is it shaking. Okay, so what they do is they have a machine, and it has a needle that goes back and forth. and then they measure at the widest part. Okay, so that's where they get their numbers, and this tells us how much it was shaking. So the question is, use this formula, and it's read in millimeters, where R is the magnitude of the earthquake on the Richter scale. Determine the magnitude of an earthquake with a seismographic reading of 23,750 millimeters. So that is our X value. So that's our log of 23,750 divided by 0.001. Okay, so that will give us the Richter scale. So what you want to do is you want to go 23,750 divided by 0.001. Have all the zeros, yes. And that answer is log of 23,750,000. Okay, so you can do this a couple different ways. You can go ahead and calculate that and then take the log of it, or as long as you put parentheses around this whole thing, it will work. So log of 23,750 divided by 0.001, and then make sure you close it. So this one, the Richter scale is 7.38 if we're rounding to two places. Okay, so 7s on the Richter scale can cause major damage. All right, my brother just texted me just last night, oh, just had an earthquake, it was a 4.9. So that one, it shakes you, but it doesn't cause any damage. So the next question is, what is the amount of intensity, or what is the seismographic reading when of the earthquake off the coast of Japan in 2011, which measured 9.1. So this is the one, most of you were probably very young, but this is the one that caused that horrible tsunami. So it was a 9.1 earthquake in the ocean, and it created a wave of water that took out many of the islands by Japan and in Japan. So Richter scale is 9.1. We're looking for the seismograph reading. Okay, so this one is set up a little bit differently. So we need to make sure that we understand all the parts. Log is base 10. 9.1 is the exponent. This is what that equals. Okay, so again, just rearranging it. Log is base 10, this is the exponent, and this is the total. Okay, so now we're just going to solve it. So you're going to go, you want x by itself, so this is x divided by 0.001. So to get rid of a divided by 0.001, we're going to multiply by 0.001. So you're going to go 0.001 times 10 raised to the 9.1 gives you 1258925.41. So that is 1,258,925 millimeters. Okay, so you can see how much it went. For the 7.3, it was 23,750 millimeters. For the Richter scale of 9.1, it was 1.3. Well, I'll just write it out. It was 1,258,925.41 millimeters. Okay, so the idea is, because it's base 10, every number, every jump up, it is shaking tenfold. Okay, so every time you jump up a number, it is now tenfold, 10 times the intensity that it was the number prior. Okay, so those are the only formulas that you need, and that's it for inverse functions, log x and 10 raised to the x power.